Welcome to another deep dive. You know I love Tyson's Astrophysics for people in a hurry.
It's such a good one.
So we're tackling the first chapter today. I've always wanted to get a clearer picture of the early universe.
The very beginning.
And it all starts with the Big Bang arc.
Of course.
I bet you picture it one way, but Tyson throws a curveball almost immediately.
What do you mean?
Well, we all think of the Big Bang
But
as this instant burst of light and galaxies.
Yeah, the glorious, But according to Tyson, the universe was actually dark.
Dark.
For a really long time, like 370,000 years.
Wow.
Which doesn't really sound very Big Bang, does it?
Doesn't at all. It's kind of counterintuitive, right?
Yeah.
You've got this universe smaller than a pinhead, unbelievably hot,
So dense.
expanding rapidly, but no light show. So what was going on during this cosmic dark age?
Okay, so Tyson breaks it down starting with
Right.
the first fraction of a second after the Big Bang. The tiniest sliver of time.
I mean, it's just mind-boggling. We're talking about 10 to the power of negative 43 seconds.
Oh.
The Planck era.
The Planck era.
Yeah, and it's just hard to even fathom a time scale like that.
Yeah, it's completely different realm, different physics.
Right?
Where the forces that we know today, like gravity, electromagnetism, the strong and weak forces, they were all unified.
Yeah.
Tyson calls it a shotgun wedding of gravity and quantum mechanics, which...
Such a great description.
Isn't that the best?
I love it.
We just don't know how to make those two frameworks work together at those energy levels.
Yeah.
It's a mystery.
Makes my head spin just thinking about it.
Right.
But as the universe expands, it starts to cool down a bit.
A bit.
Things start to settle down and we see
Right.
the building blocks of matter emerge.
Exactly. So it's like going from a blurry, chaotic mess to something slightly more defined. And this is where Einstein's famous Im-Siwaro comes into play. Energy starts converting into particles. It's what Tyson calls the particle zoo era.
I love that. So we've got these exotic particles with names like quarks and leptons popping into existence. I remember learning about them in school.
Yeah.
But it's all a bit hazy. Can you give a quick refresh?
Sure. So leptons are things like electron,
Right.
which you probably remember from chemistry class.
Yeah.
They have a negative charge and they orbit the nucleus of an atom.
Right.
But quarks are weirder. They have these fractional charges.
Fractional charges.
Yeah.
Like what's that?
Like plus 2/3 or minus 1/3.
That's not something you learn in basic science class.
It's pretty wild. And they never exist alone.
Why is that?
Well, quarks are always bound together in groups to form other particles.
Okay.
So imagine trying to pull two quarks apart. It's kind of like a rubber band. The harder you pull, the stronger that force holding them together gets. And eventually you put in so much energy that instead of separating them, you end up creating more quarks.
Really?
It's called quark confinement.
So you can't isolate a single quark?
You got it. It's physically impossible.
Wow.
We only ever see them in groups forming these heavier particles called hadrons.
Okay.
The most familiar hadrons are protons and neutrons, which make up the nucleus of an atom.
Right. That's starting to sound familiar.
Yeah.
So those tiny little quarks are what eventually become the stuff that we're made of.
Essentially, yes.
Yeah.
But there's another crucial piece that Tyson points out. It's this balance between matter and antimatter.
Okay.
So for every particle that was created in the early universe, there was also an antiparticle with the opposite charge.
I see.
So you had electrons and positrons, protons and antiprotons, and so on.
Yeah, I always thought matter and antimatter just annihilate each other on contact.
They do.
So doesn't that mean everything should have just disappeared?
It should have. But there was this tiny, tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles.
1,000,000,001 to 1,000,000,000. That seems like such a minuscule difference.
It is minuscule.
Wow.
But without that tiny imbalance, we wouldn't be here.
Right.
Everything would have just annihilated.
Gone.
Yeah, leaving behind a universe of pure energy, but no substance. So that tiny extra bit of matter is what everything we see around us is made of.
It's just wild.
I know, it's incredible.
So what happened to all the antimatter?
That's the big question.
Did it just vanish completely?
Well, there are a lot of theories, but we're still trying to figure out exactly what caused that imbalance and where all the antimatter went.
It sounds like we're just scratching the surface of this whole early universe story.
We are. Just the beginning.
So we've gone from a unified force to separate forces.
Yeah.
From pure energy to a particle zoo.
Exactly.
It's amazing how much happened in the first second after the Big Bang.
It's mind-blowing. And we haven't even gotten to the first light yet.
Oh, that's right. This is all still happening in darkness.
All in darkness.
So how did the universe go from this dark, particle-filled soup to the brilliant spectacle we see today?
Well, that's a great question, and I think we need to save that for part 2.
So we're still in the dark ages of the universe.
Yeah.
Feels like we've covered so much ground, but we're still in the first few minutes after the Big Bang.
I know, it's wild, isn't it? And, you know, we've got protons and neutrons forming, but it's still way too hot for atoms to exist.
Billions of degrees Kelvin.
Billions.
So no atoms yet. What's stopping them from forming?
Well, it's all about the electrons.
Okay.
Remember those leptons?
Yeah.
Still zipping around like crazy?
Along with the positrons?
Exactly. They're antimatter counterparts.
Too chaotic.
Way too chaotic for them to settle down and link up with protons.
So it's still this like wild, high-energy environment.
Yeah, but the universe is expanding.
Right.
And cooling, so things are about to shift again.
Okay, so around the 1 second mark.
Around the 1 second mark.
Things cool down enough.
Enough.
For electrons to start getting attracted to protons.
You got it.
So this is where we finally get atoms.
Exactly.
The basic building blocks of matter.
The basic building blocks, mostly hydrogen atoms at this point, the simplest kind. Okay. But here's the thing. Up until this point, light hasn't been able to travel very far.
Why is that?
Well, it's been constantly bumping into those free electrons, scattering in every direction.
So the universe is like a dense fog.
Yeah, you couldn't see anything.
Even if you were somehow there to witness it.
Yeah, it's opaque.
But as those electrons get captured by protons to form atoms, suddenly light is free.
Exactly.
Wow, that's a huge turning point.
Huge.
It's like the universe suddenly switches on.
It does. It's like going from blurry to crystal clear.
And that first light,
yes,
when the universe becomes transparent, that's what we detect today as the cosmic microwave background radiation.
The CMB, exactly.
Like the afterglow of the Big Bang.
That's a good analogy.
So that light has been traveling for billions of years, stretching as the universe expands.
Yes.
Shifting from visible light all the way to microwaves.
That's right.
Wait, we can actually detect light from the very beginning of the universe.
We can.
How is that possible?
It's amazing, isn't it? It's one of the most amazing discoveries in cosmology.
So how did we figure that out?
It was kind of an accident, actually. Back in the 1960s, these two physicists at Bell Labs, Penzias and Wilson, they were just trying to get rid of noise in their giant antenna.
Trying to improve communication technology.
Exactly.
Not even thinking about the Big Bang.
Nope. But no matter what they did, they kept picking up this strange signal coming from everywhere in the sky.
Really?
They even thought it might be pigeon droppings messing with their equipment.
Pigeon droppings. That's hilarious.
I know, right? What an unexpected twist.
It is. But eventually they realized that this signal wasn't coming from Earth.
Right.
It was coming from the universe itself.
The leftover radiation from the Big Bang.
Wow, so the CMB is basically an echo of the Big Bang.
That's it.
Stretched out over billions of years.
Yep.
And now detectable as microwaves.
That's the CMB.
Wow, it's incredible that we can see that moment today.
I know.
Billions of years later.
It really is.
So we've gone from a universe dominated by energy to one where matter is taking center stage.
It is.
And light has finally made its grand entrance.
The grand entrance.
All of this before the first star.
Before the first star.
Even had a chance to ignite.
It's crazy, right?
It makes you appreciate how much had to happen.
I know.
Before the universe as we know it.
Before it all
could even begin to take shape.
It's all connected.
It's all connected.
So this brings us to a really interesting question.
Okay.
What happened to all that hydrogen gas?
Yeah. How do we go from a universe filled with mostly hydrogen atoms to the dazzling display of stars and galaxies we see today?
That's where things get even more fascinating. We need to talk about gravity and the birth of the first stars.
So the universe has gone from this tiny, scorching hot speck to this vast cooling expanse of mostly hydrogen gas.
A sea of hydrogen.
Light can finally travel freely.
Right.
But it's still pretty dark and empty.
Yeah.
So how do we go from this point to the brilliant star-filled universe that we know and love today?
Well, it's all thanks to gravity, that invisible force that shapes the cosmos.
Right.
So even though that hydrogen gas was spread out incredibly thin, there were still tiny variations in its density.
Oh.
Some areas were slightly denser than others.
I see.
And these almost imperceptible differences, they were like the seeds of the first stars.
So these pockets of slightly higher gravity,
exactly.
they start pulling in more and more hydrogen gas.
It's like a cosmic snowball effect.
So they're getting denser and denser.
Denser and denser, yeah.
All this hydrogen gas rushing inwards. What happens as this material gets squeezed together?
Well, things start to heat up. The pressure and temperature at the center of these collapsing gas clouds, we call them protostars.
Protostars increase dramatically.
So they get so hot and dense that nuclear fusion ignites.
You got it. The engine of stars.
So that's where hydrogen atoms are forced together to create helium.
Right.
Releasing a tremendous amount of energy.
And that energy, that's what makes stars shine. That's what lights up the universe.
So these first stars, the pioneers of the cosmos,
yeah,
they were born out of the simplest element in the universe.
Hydrogen.
And their fusion creates heavier elements.
Heavier elements like helium.
Adding to the complexity of the universe.
It's a chain reaction of creation.
And as these first stars live out their lives, some of them explode as supernovas.
Right.
Scattering these newly created elements out into space.
Exact.
So it's not just about creating light.
No.
It's about enriching the universe with the building blocks for everything else.
Planets, asteroids, comets, even eventually life itself.
We are stardust.
We are stardust.
And those scattered elements, they mix with the existing hydrogen.
Right.
And they become part of the next generation of stars and planets.
So it's this beautiful cycle of cosmic birth, death, and rebirth.
Exactly.
It's awe-inspiring when you think about it.
I know.
Every atom in our bodies, everything we see around us, it all traces back to those first stars.
Billions of years ago.
That ignited in the darkness billions of years ago.
It highlights the interconnectedness of everything.
Doesn't it?
We're not just observers.
Yeah.
We're participants in this grand cosmic story.
That's one of the things I love about Tyson's book.
Me too.
It makes you feel like you're a part of something much bigger than yourself.
It really does.
And it makes you want to keep learning and exploring.
Absolutely. And there's so much more to explore.
There is.
Even with all that we've learned, there are still so many mysteries.
About the early universe.
Yeah. Dark matter, dark energy. The very first moments after the Big Bang.
Those are puzzles for future generations to solve.
I can't wait to see what they discover.
So we started this deep dive with the image of the universe hanging out darkness for 370,000 years.
Before the first light.
Before the first stars ignited. And learning about how those stars came to be, how they literally lit up the cosmos.
Yeah.
Seeded it with the building blocks of everything we know.
It's mind-blowing.
Pretty darn mind-blowing.
Makes you wonder what those first stars saw when they ignited.
Yeah. What did a universe without galaxies, without planets,
without heavy elements,
even without heavy elements, look like?
That's a great question to ponder.
It is.
Yeah.
That's a perfect note to end on. Thanks for joining us on this journey through the first chapter of the universe's epic story. We hope you learned something new and that it sparked your curiosity to keep exploring the cosmos. Who knows, maybe you'll be the one to unravel some of those remaining mysteries.